Okay, I'll have this all posted for you after class so you can get all this stuff back. It has to do, believe it or not, with Ireland. Go ahead and read the newspaper announcement from 1899. In the paper 100 years ago, Guinness, at the time of microbrew, essentially, needed a quality control engineer. As long as you worked from the south side of Dublin, everything was fine. Or a redneck. Solid. So the idea is, why did they need a quality control? Why do breweries need quality control testers? Just lame excuses for your buddies to come down and get a job and get loaded? Consistency. Yes, here's the deal. Here's the deal. The gentleman that got the job was named William Gossett. William Gossett. Date of hire, 1899. Here was his job description. Check it out. And the obvious challenge, of course. This is great. This is awesome. So the problem is, because Guinness was A, a microbrew, and B, it's alcohol, when he was analyzing the crops for yields across consistency of the crops, he couldn't draw the entire population, because you can't take all the wheat and all the barley and all the rye, whatever else they use in Guinness. I'm probably using the wrong grains. You can't take it all, because you can't make beer. So he could take very small samples. So in other words, he wasn't getting a large enough sample to control the margin of error. We've had this discussion before about sample sizes. Sample size is large, margins of error shrink. Well, when he had extraordinarily small samples, he needed a way to mitigate that. So he went home and thought about it. And his solution was, okay, so I can't use the normal distribution. I can't use the normal distribution. Okay, that's out, because my samples aren't large enough to justify using it. What can I do instead? So his proposal was, let me make up another one that does the same thing, that's bell-shaped, that has endpoints that I can poach for confidence and things like that. So here was a solution. Here was a solution. It's called the t-distribution. Usually we just call it the t-distribution. He called it the student's t, and I don't know why, honestly. I have no idea why he called it that.
Maybe he was drunk.
He was probably drunk when he did it. That's good. That's good. It's not how the word student popped out of his mind first. Good, Daniel. So here's the deal. He made a distribution up when, if you look at the formula he came up with, which I'm amazed by this. It boggles my mind. He came up with this by doing Monte Carlo simulation. Remember the Excel stuff I had you guys do in 243, pressing the F9 button? Well, this is 1899. There was no F9 button. There were no buttons. There were pieces of paper and a hat. And he did the same thing you guys did, except he did it manually and kept track of the results.
Wow.
So he drew these little tiny small samples and generalized an equation from those. If you look at that equation, check out the variables. There are only two variables. One of them is t itself, which is his choice of variable. That's going to be the position along the axis. So that would be the same as x in the normal distribution, where your x is. What's the only other variable in there? And it occurs a lot. There's an n, an n, an n, an n. The only variable that he discovered was sample size, which means the curve changes as a function of sample size. That's slick. The bell curve doesn't. The bell curve is always 2 standard deviations, 95% confidence. 1 standard deviation, 68% confidence. 2.575 standard deviations, 99% confidence. Always. This one changes depending on how large your sample is. Fascinating. Now here's why we care. Maybe you don't. That's okay. That's okay. The reason is, at smaller sample sizes, it controls for the uncertainty better than the z distribution does. Okay? So what I'm going to show you here, I hope this will work. Will it open? It might not. I may have to check it. Nope. That's okay. I've got it right here, ready to go. So let me shrink this down. What I've done here, see if you guys can see what I'm trying to get you to see. Insert here. So what I've done here is I'm graphing the t distribution, which is the red one, alongside the normal distribution, which is the blue one. And what we're going to do is we're going to mess with the sample size. We're going to change the sample size, and we're going to see how it affects the shape of the distribution. Now, first of all, how are the z-curve and the t-curve the same? How are they the same? How are they similar, I should say, not the same. How are they similar?